Hi everyone. Today I'd like to talk about probabilistic scheduling, which extends our previous HOS framework called DAS. In this talk, I will briefly introduce DAS, and then I will walk through a simple example and show the problem that we try to solve. Finally, I'm going to show how we efficiently solve the problem using probabilistic analysis. Okay, so what is DAS? DAS stands for Dynamic and Static Scheduling. For those who are not familiar with high-level synthesis is a process that automatically translates high-level program like in C or C++ into a low-level hardware description like Verilog or VHDL. So we can get a custom hardware in ASIC or FPGA. Traditionally, HOS tools use static scheduling, which determines the time behavior of hardware at compile time. And this is amenable for programs with simple control flows. Recently, there are HOS tools that dynamically schedule the hardware using additional handshake interface. And this is amenable for programs with complex control flows or dependencies. So both of them have advantages and disadvantages. Our previous work thus proposes an approach that combines these two static schedulings in a single circuit to maximize both their advantages. As we know, we can do a lot of optimizations for the statically scheduled hardware because everything is known at compile time. However, we wonder whether we could take the information in the dynamically scheduled circuits as additional constraints to further optimize the statically scheduled circuits. And this is actually challenging because we only have the limited information for the dynamic features before actually running the hardware. Let me try walk you through a simple example which may lead to complex design choices. Say Homer wants to synthesize the program on the left through DAS. The program does vector transformation. In a for loop, the data address G is overwritten by the function of ssfunc of array elements at I. The function ssfunc is a simple polynomial expression with no control flow. So Homer chooses to statically schedule this function. And the function vectrans, a loop loads an array element AI and then writes ss function into AG, where G depends on the loop iterator I and array B. So there is a memory dependence between AG and AI. Because the expression of G is data dependent, it is difficult to statically analyze the dependence between two addresses, G and I. So Homer leaves this function for dynamic scheduling, so the hardware can schedule the memory at runtime. Here is the synthesized circuit. The red block is a dynamically scheduled circuit with a set of predefined components connected to using handshake interface. The green block contains a statically scheduled circuit where a finite state machine is used to control the registers and operators. In static scheduling, it is common to pipeline the hardware for improving the throughput. In this example, Homer also wants to pipeline the function ssfunc, but it is difficult to choose an probe II for this function. Of course, we could pipeline it with an RF1, but it would be a waste of resource if the external circuits cannot feed the input that fast. Choosing a larger II will stall the pipeline and make the performance worse. We know Homer, he surely doesn't want to do that by himself. So is there any existing analysis that can help us to determine an optimal II? So I have got some results for him. If we synthesize the whole design through Vitus HOS, the tool will suggest not to pipeline the function as its func, because the memory dependence could make the loop iteration sequential, and the Vitus HOS conservatively choose the largest II, which equal to the latency of the function. If we synthesize the whole design through Dynamatic, which is the HOS tool that generates dynamically scheduled circuits, the analyzer in Dynamatic ignores the input dependence, so it suggests an II of 1. This is a huge difference, isn't it? Basically, if we can only choose not to share any resource or sharing every resources. There must be an optimal II between 1 and 15, which has the best performance and smaller area. But how do we find it? How about simulation? Yeah, if we run simulations, we know how fast it is likely to compute. The figure on the right is the optimal II for all the input distribution. So we can see the optimal II actually varies with the distribution of if condition and the dependence distance between G and I. This figure is measured using exhaustive search, which took a long time. And the search time scales exponentially with the code complexity. Of course, we don't want to find an II by trying every simulation cases. This brings our goal. We want to have a generic technique to describe the behavior of hardware, and this technique should allow us to efficiently explore the dynamic features under compile time. Particularly for this problem, we want to estimate the performance of the hardware in both transient and average cases. So if we rethink the problem of finding an optimal II, it actually can be a probabilistic problem. Having a small II will ensure the circuit runs at a fast speed, but the resources may not be well utilized. Having a large II may explore more resource sharing, but may cause pipeline stalls. However, with any II, the hardware will still produce the same results, which allows small discrepancies in our probabilistic analysis. To model our hardware behavior for probabilistic analysis, we use Petri nets. Petri nets are a common mathematical model for the description of distributed systems. It consists of 5 features. A place, usually represented by a circuit or a circle, is a placeholder for state. Places may contain tokens, indicated by dots. By default, each place can hold at most 1 token. A transition, usually represented by a bar or rectangle, is a process. A timed transition always fires with a single cycle delay, and an immediate transition always fires with no delay. Each edge always connects a place and a transition. For example, the Petri net on the left will propagate the token to the right. Because the second transition is the immediate transition, which has no delay, the whole process takes only 1 cycle. Note that our model only models the presence of data instead of the exact values, because we only need to analyze the time behavior of the hardware. With these 5 elements, I will show you how to model the time behavior of arbitrary HOS hardware. First, the behavior of a statically scheduled circuit is predictable, which is determined under compile time. The circuit on the right shows an example of statically scheduled circuit. It has n in inputs and n out outputs. The circuit has a back edge that contains II time transitions to ensure the maximum throughput of the circuit. And the total number of the time transitions between the inputs and outputs is the latency of the circuits in cycles. Now let's see how this model behaves. The first transition requires all the input plates to have tokens to be filed. So in this case, the transition waits until all the inputs to be valid. Now if all the inputs are valid, the transition fires, which also consume the token in the back edge. The propagated token is then going through a chain of time transitions towards the output. The pipeline circuit may have a few set of inputs being valid at the input ports. However, because the time difference is smaller than the II in this case, the circuit is not ready to consume the new set of data. In Petronet, it is blocked by the empty purple place. The token in the purple place will be reproduced when the first set of data in the form of token will be consumed by the ith transition, which is shown in red. After that, the purple place enables the input transition, so the second set of data will be processed by the circuit in the next clock cycle. And this repeats every II cycles. When the token reaches the last transition, which it takes L-1 cycles, the output transition consumes the token and generates a token for each of its output plates. And this indicates the completion of one computation of set data. So this Petronet models 4 features of a statically scheduled circuit: the input count, the output count, the II, and the latency in cycles. For dynamic scheduling, the output circuits are made of a netlist of set of predefined components. So we model each predefined components in Petronet. So any dynamically scheduled circuit can be modeled by connecting these Petronet units. Once we construct a Petronet for an input program, the analyzer explores all the possible states of Petronet, resulting in a state diagram, also known as reachability graph. For instance, an accumulation process in a for loop results in the state diagram on the right. So the program starts at M0 as the initial state, and then it checks whether to enter the for loop at M1. If the loop is skipped, it goes to M15 and eventually goes back to M1. If it enters the loop, it fills the pipeline till M4 and iteratively computes addition on S. The addition takes 4 cycles, so the state diagram has a loop of 4 states, indicating an II4. Once it exits the loop, it exits the pipeline in a few cycles and goes back to M1 for a new round of computation. So M5 indicates how frequently the loop computes, which provides a weight for the steady states of this diagram. So we can see the steady states of the circuit is the most inner loop of 4 states. So we know the II of the adder should be 4. Our tool flow is shown here. Firstly, the front end of DAS takes C program and splits it into 2 groups for statically scheduling and dynamic scheduling respectively. When the Petronet model is constructed, including the best possible performance configuration of statically scheduled components. The analyzer then gives an estimated throughput of the statically scheduled components, so we can update the II with the most likely optimal IIs to save resources. We evaluate our approaches over 6 benchmarks compared to the extreme IIs given by Dynamatic and Vitis HOS, we achieve better area delay products than both tools. The figure shows the normalized result in area and delay. Overall, the analysis in Vitis HOS loses performance but has a small area. The analysis in Dynamatic has larger area and comparable performance with our tool. So we also compared our approach with exhaustive search, and our work achieves almost the same area delay product, but 9 times speed up in search time. Thanks. Now I will be taking questions.